Good evening and welcome back to Space Nest. Tonight we are done with the fluff pieces and the press releases that tell you everything is normal. We are dissecting a physics puzzle that is currently playing out at 70 kilometers per second. If you have been paying attention to the raw data streams, you have heard the name 3I Atlas. It is officially the third interstellar object catalogued by humanity, following the confusing arrival of Oumuamua and the more standard appearance of Borisov. But if you think this is just a replay of those previous encounters, you need to look closer at the numbers. The narrative they are feeding you is about where it came from, but that is a distraction. The real story here is not about its origin in some distant star system. It is about what it is doing right now, right here in our own backyard. The initial detection was standard, the kind of thing that happens every night at observatories around the world. Telescopes picked up a faint point of light drifting against the background stars, barely registering above the noise floor. But as we tracked it over several months, the light curve began to misbehave in a way that should make every astronomer sit up and take notice. It wasn't a steady, tumbling rock reflecting sunlight in a predictable pattern. It was active. We are talking about sustained outgassing of gas, dust, and plasma on a scale that defies its size. Now, comets do this all the time, and usually it is not news, but 3I Atlas is doing it while moving on a hyperbolic trajectory at velocities of roughly 60 to 70 kilometers per second. That speed is the first massive red flag that tells us something is wrong with the standard model. It tells us unequivocally that this object is not bound to our sun. It is a visitor punching through the solar system with incredible kinetic energy, treating our gravity well like a minor speed bump. And yet, despite this dominant motion and high velocity, it is shedding mass in a way that defies simple thermal models. We have photometric and spectroscopic observations from ground-based giants and space-based platforms like the James Webb Space Telescope. These instruments paint a picture of collimated jets. These aren't the diffuse, fluffy clouds of gas you might expect from a sublimating snowball. These are directed streams of material shooting out from the nucleus like exhaust from a nozzle. And this is where the visualization gets interesting and terrifyingly complex. Imagine a bullet flying through the air at supersonic speeds, but this bullet is spinning and venting high-pressure gas in specific, calculated directions. That venting acts like a thruster. It is a natural rocket engine, but the physics governing it are chaotic, raw, and violent. This activity has produced what astronomers call an atypical tail morphology. In a standard comet, the tail points away from the sun, driven obediently by the solar wind. But 3I Atlas is different. Its tail structure is complex, suggesting that the particles being ejected are heavy, or alternatively, they are being launched with a significant velocity of their own independent of solar radiation pressure. This contradicts what we previously thought about how small interstellar bodies should behave when they get close to a star. We assumed they would either remain inert rocks or disintegrate into dust. 3I Atlas is doing neither. It is evolving, reacting to our environment in real time, and the mechanism behind it is baffling the experts. Why does this collimation matter? It matters because of the energy budget required to sustain it. For an object to maintain directed jets while traveling at hypersonic interstellar speeds, the internal mechanism must be robust. We aren't just seeing surface ice boiling off in a gentle fog. We might be seeing pockets of volatile materials that have been frozen for billions of years in the deep void, suddenly exposed to the searing heat of our sun, creating an immense thermal shock. But the spectroscopic data is showing us something else entirely. It is showing us plasma. The outgassing isn't just neutral gas drifting away. There is an ionized component that shouldn't be there. This implies high-energy interactions, possibly magnetic or chemical, occurring right at the surface of the nucleus. Here is the crucial detail that separates 3I Atlas from its predecessors. The data indicates that this mass loss is significant enough to alter the object's trajectory slightly. This is what we call non-gravitational acceleration. But unlike Oumuamua, where the acceleration was subtle and mysterious, here we can see the engine. We can see the jets firing and map the plasma distribution. The mystery isn't what is pushing it, because the mechanics of propulsion are visible. The mystery is what it is pushing out. The velocity of the ejected material is the key variable that changes everything. When a jet fires, the particles don't just sit there. They are launched, and because the parent body is moving so fast, we have a complex vector addition problem. You have the velocity of the nucleus at 70 km/s, and then you have the plus or minus velocity of the jet itself. That plus or minus is everything in orbital mechanics. If a jet fires backward against the direction of travel, those particles leave the nucleus slower than the nucleus itself. They are effectively braking relative to the Sun. This means that 3I Atlas isn't just a lonely traveler passing through the night. It is a cedar. It is leaving a footprint, distinct from a classic dust trail. Because of the high orbital velocity and the high ejection velocity, the spread of material is massive. We are looking at a cloud of debris that is expanding and shearing apart under the influence of gravity. The nucleus will leave the solar system, never to return, but the material it has ejected is a different story. We tend to think of space as empty and interstellar flybys as clean events: entry, exit, done. But the physics of 3I Atlas suggests a messy encounter. It is dumping tons of material, gas, dust, and plasma into the inner solar system. This material doesn't just vanish, it has to go somewhere. It creates a structure in space, a ghost of the object's passage. As we established, 3I Atlas is shedding material via collimated jets at tremendous speeds. Here is where the math gets fascinating. If a backward-firing jet is powerful enough, it subtracts enough speed from the dust grains that their heliocentric velocity drops. This effectively puts the brakes on that specific fraction of the ejected material. While the main body retains enough energy to escape the solar potential well, the dust in the tail does not necessarily share that fate. Some fraction of the released matter may remain temporarily bound. We are talking about a phantom trail, a diffuse, extended structure of interstellar material that gets left behind, caught in a gravitational limbo. The nucleus checks out of the hotel, but it leaves its luggage in the lobby. This trail isn't a tight line. Because of the variety of particle sizes and ejection speeds, the trail shears out into a complex three-dimensional ribbon weaving through the inner solar system. The evolution of such a trail is governed by more than just gravity. First, we have radiation pressure. Photons from the sun hit these grains and physically push them. For very small, fluffy particles, this pressure blows them out of the system. But for larger, denser grains, gravity wins. Yet the orbit is modified. Then we have the Poynting-Robertson effect, a subtle relativistic drag force that causes dust grains to spiral inward toward the sun over time. But the real game-changer for the 3I Atlas trail is the electrostatic properties of the dust. In the vacuum of space, sunlit dust becomes electrically charged as ultraviolet light knocks electrons off the surface. Once charged, these grains stop acting like simple falling rocks and start acting like charged particles. They interact with the solar wind and the interplanetary magnetic field. This allows for clumpy density inhomogeneities and localized dusty plasma structures. Magnetic field lines can trap or funnel these charged grains, creating filaments of interstellar particles held together by electromagnetic forces. This completely changes our modeling. We aren't seeing a smooth cloud, but a dynamic entity breathing and shifting with the solar wind. This brings us to the composition of the dust. If this were a normal comet, we'd expect silicates and standard carbon chains, but 3I Atlas is showing spectroscopic indications of enhanced metallic content, particularly nickel and iron. Metallic grains are conductors, and their photoelectric yield is much higher than an insulator like rock. These grains acquire high surface potentials, becoming highly charged little capacitors. A highly charged metallic grain moving through the Sun's magnetic field feels a Lorentz force, the same force that curves paths in a particle accelerator. If this force is strong enough, the trajectories become non-Keplerian. They can be deflected, channeled, or scattered. The magnetic field can act like a lens, focusing the dust into streams or sheets. Imagine iron filings on a sheet of paper with a magnet underneath. Now scale that to millions of kilometers. You get a dusty plasma structure that is invisible but has significant particle density. This implies the trail is resilient. Even months after the nucleus has passed, these coherent structures of metallic dust could persist. And when we plug in the variables for charged metallic dust interacting with the solar wind, the simulation spits out a date and location for a probability map. Orbital geometry implies that in the upcoming months of March and April, a specific planet could intersect a portion of this residual trail. Earth. This isn't a head-on collision with the nucleus. That's safely far away. This is Earth passing through the wake like a ship crossing ripples, but we have to consult the landlord, Jupiter. As the ejecta stream passes near the gas giant, Jupiter's massive gravity acts as a chaotic scatterer, potentially stripping dust away or focusing it like a slingshot. Furthermore, Jupiter has the most powerful magnetic environment in the solar system. Passing near it is like walking through a magnetic storm, which could alter the charge state of the particles and influence their evolution. This introduces uncertainty, but the spread of material is so vast that it is highly probable Earth will cross through some density of this matter. We are looking at a rendezvous between our planet and matter born around another star. This is a one-time event. The trail is a transient feature. As Earth moves through its orbit in early spring, we effectively sweep through the zone where the trail is calculated to linger. We aren't talking about fireballs raining down, but subtle, measurable interactions with Earth's complex systems. We would likely see modest changes in the micrometeoroid background, a spike in the tons of dust that hit our planet every day. For the average person, you might notice nothing, but for scientific instruments, this is a gold mine. We could see ionization levels in the upper atmosphere fluctuate as high-velocity dust vaporizes into free electrons and metal ions. This connects to our infrastructure. Aerodynamic drag on satellites could increase slightly due to particle impact drag. For satellite operators, it's a variable that needs tracking. In less likely but physically permissible scenarios, we cannot exclude localized disturbances of the plasmasphere or pitting on solar panels from micron-sized nickel grains hitting at orbital velocities. This is not a prediction of catastrophe, but a testable hypothesis. 3I Atlas offers a rare opportunity to observe interstellar material touching our world. The central scientific question is whether we will deploy sufficient measurements to turn informed speculation into data. Are we looking with the right radar settings? Are we monitoring the ionosondes? This is how science advances, by recognizing the moment the universe offers a clue. 3I Atlas is that metallic, outgassing, high-speed messenger. If you found this deep dive valuable, please leave a like. It tells the algorithm people want real science news. We will be monitoring the atmospheric data as we get closer to those March and April dates.